In section 9.6, we're going to move a little bit past the ideal gas law here and take a peek at the way that we can handle non-ideal behavior. So we're going to describe the physical factors that lead to the deviations from the ideal gas behavior. We'll explain how these factors are represented in the van der Waals equation. We'll define compressibility and describe how its variation with pressure reflects non-ideal behavior. And we'll quantify non-ideal behavior by comparing computations of gas properties using the ideal gas law and the van der Waals equation. So, as we've been talking about, we need to make a number of assumptions about a gas to consider it ideal. The pressure has to be relatively low. The temperature has to be pretty high. The gas molecules do not occupy any space, and they do not interact with one another. In practice, though, gases rarely meet these requirements, so we can't really consider them ideal. When they don't deviate from ideal behavior, will be observed. Compressibility is one way that we can kind of detect and quantify how much a gas is deviating from ideal behavior. And so the compressibility factor is the ratio of the volume of 1 mole of a real gas to the volume of 1 mole of ideal gas. The two gases must have the same temperature and pressure. So we get the molar volume of a real gas divided by the molar volume of an ideal gas. And molar volume means the volume divided by the number of moles. And you see that you put these little carets above it when you have the molar volume. So if we have the molar volume of the real under the ideal, we know that this term for an ideal gas would equal RT divided by P, and we see that Z is equal to PV real divided by RT. So essentially the ideal gas law with the actual volume plugged in. When a real gas behaves ideally, the compressibility factor is going to equal 1. This numerator is going to be the same as the denominator here. When a real gas deviates from ideal behavior, the compressibility factor is more or less than 1. And the compressibility factor can be used to determine how ideal the gas is behaving and therefore how valid using the ideal gas law is. We can picture here some Z values for some common gases at different pressures. And you can see that sometimes it may deviate very much so, either negatively or positively. And these are just kind of heading off into infinity here where we're really, really high pressure and the ideal gas law breaks down. But even within a realm where you might think it would work, sometimes we see quite a bit of deviation. CO2 here, for one, is one that's deviating quite a bit, probably because of intermolecular forces where the CO2s are interacting with one another. So when the pressure is low, gas molecules are far apart. The volume of the molecules themselves is insignificant compared to the overall volume. When the temperature is high, the intermolecular forces of the gases are so low relative to their kinetic energy, the molecules' trajectories are unchanged by neighboring molecules. But when that isn't true, the molecules are forced together, the volume of the gas is no longer insignificant, and intermolecular forces start, and when the temperature is low, intermolecular forces can cause deviations in the atoms' trajectories. And we can kind of picture that here. As we start to shove them together, we're getting all these interactions that are going to cause different trajectories for the gas molecules. And finally, we're going to talk just a little bit about the van der Waals equation. This is a more sophisticated model of gas behavior. It includes the parameters A and B to correct for the intermolecular forces interactions and molecular volume. The value of A and B for a specific gas can be determined experimentally. So we have this equation here. This is one of the so-called cubic equations of state for gases. There's a few of them, Dieterach's and the virial expansion and stuff. And what they're really trying to do here is that if you look at A here, this is accounting for the molecular attraction. So it multiplies times n squared, and it kind of gives you the sense almost like there's more molecules interacting, that their interaction is a little bit more, it's going to make this term larger. And then over here we see a correction on the volume, and this is to correct for the volume of that gas. Basically what they do is they do a whole bunch of experiments and they graph them all out, and they use that to determine what A and B would be for that gas. And you can see that they've got some tables where they plug in these A and B values so that you can use this to determine properties just like you would this guy here. They're a little tricky. Like you can see that the pressure wouldn't be too crazy, or the temperature wouldn't be too crazy to get at here. But solving for the volume is a particular problem. These are called cubic equations because if you factored this all out, you'd actually wind up getting a cubic equation that you'd have to solve, which doesn't really have an analytical answer. You'd have to like get out the calculator and do like a numerical method for solving that.